Good morning, Energy Conversion Conservation class. I'm going to record a lecture this morning and post it for class today. We're going to delve into compressed air systems starting today, probably for most of the rest of the semester. And so this will be the first of those lectures. So compressed air efficiency is the title of the presentation. I'll email this out to you with this link. So, of course, layout. We'll have a brief introduction. We'll talk about the generation of compressed air, the conditioning of compressed air, distribution, and end uses for compressed air. I've got a nice little kind of a cartoon of a system here. It is a fairly realistic, I must say. We show a couple compressors, maybe operate one, have one in reserve would be a good idea. We're concerned about moisture inside the line, storage tank, and getting into controls and things. So we have a moisture separator right out of the compressors. Then we have a air receiver tank. In this case, this is storing wet air, as we'll learn. We come out and we have some filter. We have a filter. We have a dryer to remove as much moisture as to give us the level of dryness that we think that we need in the system. And then we have a final filter. This is an oil water separator because these are typically what we'll talk about as lubricant injected compressors. And so this water that condenses out will probably have some compressor lubricant in it. So we can't just put that directly down the drain. So we need a separator. We go out to our system and then we feed up, and our distribution system is actually a loop, which turns out is a very, very good idea. We show some taps coming off of the top. You really don't want to come off the bottom if you're bringing things down any more than you have to, because that's where moisture and dirt and such will accumulate. So anyway, that's just neither here nor there, I guess. Introduction. Topics we're going to discuss, types of industrial air compressor, excuse me. Understanding compressor controls, compressed air treatment, dryers, filters, drain traps, air receivers and storage, compressor selection and sizing. We'll talk about minimizing pressure drop through your distribution system. Compressed air leaks. Some are actually planned based on the type of equipment that you select. Inappropriate uses of compressed air, and a summary. Okay, so if you've worked or co-op or interned in a production facility, you realize that the people out there making stuff on the line, doing maintenance, etc., they consider compressed air to be free because they don't have to pay the utility bill. But compressed air is usually the most expensive site utility of the common ones. You may have something special that you're at a particular plant, which may be more expensive. But generally speaking, compressed air is pretty expensive as an energy source. So you see signs like this: caution, do not use compressed air to blow off clothing. It's also can be a safety concern. Compressed air has costs that can be controlled and minimized. And I don't know, I found this picture out there of Benjamin's flowing with a leak of compressed air. As we'll see, there are a significant number of compressed air leaks out there in most facilities that need to be managed. You need to have a program where you find those things and fix them. Okay, so This is the relative cost slide. And, you know, we look at natural gas these days, and natural gas may even be cheaper these days. Depends on how much you buy and where you are. I would say these days, natural gas is probably $3 to $7 an MCF, but 5 to 7 is still. And an MCF that's 1,000 cubic feet, and a cubic foot is 1,000. 1,000 is a million, and MM stands for million BTUs. So, say $5 to $7 a million to buy energy in the form of gas. Electricity at 8 cents is $23.44 a million. You take a million divided by 3412, that's the conversion from kilowatt hours to BTUs, and then multiply by 0.08, and you get 23.44. So we can see electricity is considerably more expensive when doing a comparison per million BTUs of energy delivered compared to natural gas. And then we state the fact that on average, 7 horsepower of compressor input power is needed to produce the compressed air to operate a 1 horsepower pneumatic motor. Well, so that says that if this is our cost of electricity to deliver energy with a pneumatic motor, it's going to be 7 times that. So 7 times this is roughly $164 per million BTUs of delivered energy with that pneumatic motors. Pretty expensive. Okay, if you look at the where the energy that goes into an air compressor, where it winds up, we've got this little bar chart over here, which is, you know, not bad. So the bar on the left, input power to the electric motor. So this includes the motor inefficiency and everything. So in this case, and this is to obtain 1 horsepower of pneumatic work output. So you see in this case, if you take the inefficiency of the motor into account, it may even be more than 7 horsepower. But anyway, if you look at shaft power, then that comes out roughly 7, someplace around 7. And of that energy, power losses and useful work, the useful work is in terms of the pressure. You know, that's what we use, because that in the process of compressing the air, it gets really hot, and we typically throw away the heat. Well, this is maybe 15 to 20% of the energy, and that gets used in terms of pressure. And this is the amount of energy that we throw away in terms of heat. So you see, we put this in and we get this out. Now, that should be becoming pretty clear that from an energy standpoint, compressed air is it's handy and it's easy to plug hoses in and move stuff around, but it's not very efficient. Okay, and here's I put this little example in a while ago. I went out and I searched for a 1 horsepower pneumatic motor. And I don't know why they sized them this way, but this one was 0.93 horsepower, 300 CFM, 3,000 RPM. This was on Granger. A couple years ago, you could buy this for less than $300. I was looking for the airflow, so max airflow, when this thing is putting out its full rated load. And I'm sure this is 100 PSI air. That's a pretty standard number. But we need 30 cubic CFM is cubic feet per minute of air. Okay. Well, let's look at how we can do a little calculation here. And we see that typical compressor specific power, and these are like efficiency ratings, miles per gallon or something like that, kW per 100. So that would say that for this a common, and this is a fairly efficient compressor, it takes 20 kW to produce a flow rate of 100 CFM. Or if you can convert the 20 kW into brake horsepower, divide by 0.746, and I think you get 26.8 brake horsepower per 100. There's the conversion factor. So to supply 30 CFM requires 30% of this, which is 8.04, or it requires 30% of the 20, which is 6 kW. So let's say electricity would cost 8 cents a kilowatt hour. If you just multiply that out, you get a little over $4,200 a year to produce the compressed air that it takes to operate this one. In fact, it's 0.93 horsepower pneumatic motor, so it's not quite 1 horsepower. If, however, instead of using that pneumatic motor, you used a 1 horsepower electric motor with an efficiency of 83.5%, it will require 0.89 kW. If you multiply that out, it's $624 a year to operate. Conclusion, it's expensive. Now, some environments require explosion proof. You can't have sparks that electric motors produce. And so there can be reasons, portability, all that sort of thing. It's handy, but wow, it's pretty expensive. Okay, so if you look at the life cycle cost of using compressed air, so if you look at over a 10-year period, the total cost of purchasing, maintaining, and supplying energy to the compressed air equipment, we see that the equipment cost is about 12%. The maintenance cost is about 12%. And the electricity is about 76%. So if you can spend a little bit more on the front end and get a significantly more efficient compressor, it's probably worth the investment. Okay, so typical components of demand, where does the air go in a typical industrial facility? Well, 50% of the air that we produce goes to production processes, which is why we run the system. Another 5 to 10% typically goes to other uses, which are deemed inappropriate because there's better, cheaper ways to do it. Leaks account for typically 25 to 30% of the air that we produce, and artificial demand is 10 to 15%. And the next slide will define what we mean by artificial demand, but it's not necessarily a good thing. Okay, so to define artificial demand, we kind of make up a little scenario here. So if the compressed air system pressure, and you see a lot of them, could be 110 PSIG, it's like an average, in a plant where really it only needs to be 90 PSIG, then we're running 20 PSI higher pressure than we need. So every open blowing application, which basically just takes line pressure and blows it out of a tube or into some sort of a device. This is showing what we call an engineered nozzle to blow parts off. And this is a leak. This is a leak detection spray. It's like soapy water, and you spray on it. And if there's air coming out, then it bubbles up. That's one way to find them. And so if we're running a 110 when we only need 90, all of these open blowing applications that just blow compressed air out are going to blow more than at 110 than they would at 90. Well, that differential amount of air consumption blown out is what we call artificial demand, because that's demand that's there simply because we're running too high a pressure or a higher pressure than we really need. So that's this artificial demand, 10 to 15% of our total air production. Okay, language of compressed air. We'll go through some of this. PSIA, that's pounds per square inch, absolute pressure measured relative to absolute vacuum. PSIG, pounds per square inch gauge pressure, which is the pressure that would be above atmosphere, wherever the location where the gauge is measuring. CFM, cubic feet per minute of flow. ACFM, actual cubic feet per minute of flow. And so in order to calculate the volume flow rate, we need a pressure and a temperature at which we wish to state that flow, and we can use different pressures and temperatures. So an actual may be at the actual conditions in the compressor room. You could be in Denver. You have, I don't know, 12, 13 PSI atmospheric pressure. You could be at sea level where it's 14.7. Would be at different temperatures. Inlet is typically the inlet at the compressor. What conditions do we actually see flowing into the compressor? A standard cubic feet per minute would be at standard conditions, and we do have more than one standard. CAGI is the Compressed Air and Gas Institute. They recommend a standard conditions of 68 Fahrenheit, 14.5 PSIA, and dry. There's an ASME standard air condition at 68 Fahrenheit, 14.7, and 36% relative humidity. So there are different standards out there. BHP is brake horsepower. We've defined that before. That's if you have a motor operating, that's the actual amount of power in the shaft coming out, the rotating shaft coming out of the motor. And we have specific power parameters of brake horsepower to produce 1,000 CFM. I'm sorry, 100 CFM, not 1,000. And we can also state this in terms of kW to produce 100 CFM. These are some definitions of actual, inlet, and standard CFMs. I kind of just went through that, so I'll let you read those. But you do need to be comfortable with these different definitions. Conversion, we have equations kind of out of your thermo or your fluids, I guess. So let's say if you have a standard CFM and you want to calculate an actual cubic feet per minute based on some actual condition, you can use this. Or if you had an actual, then you can solve this equation to convert to a standard. And so let's see, if we have an SCFM, we multiply it by the standard pressure, absolute PSIA, divided by the actual pressure, PSIA, minus the saturation pressure, the water saturation pressure, like at the actual temperature, times phi, the relative humidity, and then multiply that by the ratio of T actual to T standard, and those have to be in absolute temperature. So degrees Rankine or degrees Kelvin. And I think we've got a little example here. Let's see, conversion of SCFM to ACFM. So we've got an elevation of 5,000 feet. So that is like Denver, 12.23 PSIA. Actual temperature is 80. Saturation water pressure is 0.5069. Relative humidity is 80%. And the air demand would be 1,000 SCFM. So under those specific conditions, that standard airflow, when you plug all the numbers in, turns out to be almost 1,300 ACFM. And that's what the compressor operating in that room to satisfy that demand, because equipment is rated, equipment that consumes compressed air has a rating. Typically it's 100 psi pressure and standard conditions. Well, you're operating in Denver, you're not operating at standard conditions, and so this would be, you would need almost 1300 CFM for all this equipment that was rated to consume 1,000 CFM standard. Okay, so consider a 300 horsepower air compressor that's drawing, say, 220 kW of input power. And let's just look at that for a second. 300 times 0.746. That's 223. Okay, just checking. We will examine the energy flows into and out of the control volume drawn around the air compressor. So this is, I found this figure out there, but it gives a pretty good breakdown. So for example, let's see, 220, so I'm just checking these flows, 5280 divided by 220. Yeah, that's 24 hours of operation. So this 5280 kilowatt hours a day is this 220 times 24. So that's what's going into compressed air generation. Okay? So where does all of that go? Well, our waste heat on this diagram is showing 3221. So 3221 divided by 5280, that's showing 61% going directly to waste heat and other losses. Okay, well, leakage, that would be leaks out in the system. And so what is that? That's not quite 10% in this case. I may or may not agree with the previous slide, but anyway, you see this sort of thing. So then we're taking equivalent to 62 kilowatt hours a day for actuation energy. We've got pneumatic actuators out there in the plant, and they require a small amount of air. The plant is usually doing some conveying. They may be blowing stuff around. May have pneumatic motors on conveyors, whatever. So that's a little over 1,092. And then we have some sort of blowing, cleaning, purging, sealing, filter pulsing, etc. for another 500 or 415. And then we've got some air, pneumatic tools, air guns, etc. So that's not a bad typical breakdown where the air might go in just kind of a generic plant. Okay, we're gonna, this is a picture of a good size industrial air compressor. And we're gonna just look at some of the power flows through this thing. So we got kind of a generic picture of this guy over here. And so we're gonna say we're gonna put 100 kW of electric energy input in. We'll get some shaft. This is the motor. This is the compressor. So we get some air in, low temperature and pressure out at higher temperature and pressure. Okay. Well, so if my motor is what, 92% efficient, and I put 100 kW in, I'm going to lose 8 kW, friction, windage, all that sort of thing on the motor. And then, so I get 92 kW in the shaft. Okay, but we note that high pressure air is a desired product from the compressor. But what do I really get? I get high pressure, high temperature air again. And so coming out of the compression element, I have a heat exchanger. where I'm going to throw roughly 80 kW of thermal energy away to the atmosphere. And then if I have a 10 to 20 kW of shaft energy output from the air motor, this is what I get out of this. And if you add all this up, we have potential to be more than 100% efficient. But that is because this air coming out here is very cold. And so I can actually, you know, if you do the actual calculations, you can see that you can get more than 100 kW out because of the thermodynamic condition of the air at the exit of this turbine. A little detail there. All right. Okay, this slide shows the ability to recover and use some of this waste heat. These are those Ingersoll Rand. I think they were 400 horsepower compressors, so a pretty good size compressor. And they're air cooled. And so what they do is they just suck air in intakes from the compressor room. And then they blow it. There's well, there are probably 4 or 5 horsepower, maybe a little bit bigger fan in here that blows that air across a heat exchanger that cools the compressed air down. We typically want to see 100-degree compressed air temperature or less exiting the compressor box. And so they built some ductwork up here. So in the summertime, there's a back wall back here. So in the summertime, they've got some dampers on this. So they throw this hot air coming out of the top of the compressor box outside because, you know, it's already too hot in the plant probably. Or if it's air conditioned, you sure don't want to air condition that heat away. But in the wintertime when it's cold, you can throw the dampers the other way and throw it out through these ducts, and it distributes it out and blows it into the facility. And this is probably the best distribution system I've ever seen. The fans in the compressor box can push it a little ways. I think these people had actually put in some additional fans to distribute this heat out through, because this was a pretty extensive duct system, which will have some pressure drop on it. So you can push it a little way, like you can push it through a wall or something like this with a fan inside the compressor box, but much more than that, then you're going to have so much pressure loss on it that you're going to reduce the airflow and you're going to have a hard time cooling your compressor properly. So we can get in the cold winter months, we can get 100, 130, something like that, degrees, which is plenty warm enough to do some effective space heating. So this was a company in Knoxville, I believe, and that was pretty impressive. I mean, we pretty commonly, I mean, I would say 10, 15% of the systems that we look at will have some sort of ducting and the ability to throw heat into the plant in the winter or get it out of the plant in the summertime. So that's pretty much that one. Okay. More comments on waste heat recovery from the compressors. Water-cooled compressors have the potential to preheat makeup water, say go into boilers or water heaters. Brigstone over in North Carolina had a big utility room, big mechanical room, and they had boilers and air compressors and all this kind of in close proximity. And they had some big air compressors, and so they were water cooled. And so they simply would treat the boiler makeup water, you know, get it ready, and then it would flow through the air compressors, and that cold water would cool the air compressor. And so they would pick up, you know, significant amount of temperature. They might pick up probably, you know, I don't know, 30, probably 25 to 30 degrees in temperature. Cooling the air compressor, and then they would take that water into the deaerator, and that would reduce the natural gas use on the boilers. I mean, it's really nice. And of course, you know, you got to have consistent compressed air demand and make up water demand on your boiler, but it was a big plant and that worked out well for them. So it took that, 70, 80% of the electrical energy that's converted into heat in the air compressor and took that and put most of it into the boiler to reduce the natural gas purchase. That's pretty smart thinking. Okay. We have, as we'll see when we get to compressor types, we have rotary screw compressors are the most common type we see these days. And we have lubricant free and we have lubricant injected. So the lubricant free rotary screw compressors typically have like a Teflon type coating on the screws to do their best to minimize friction, but it's still not as good as spraying oil. So the lubricant free compressors won't be quite as efficient as the lube injected ones. And so that extra inefficiency can generate some higher temperatures. So if you balance the water flow just right, you can get water temperatures of 150 to 175 degrees coming out of these compressors, which is pretty effective. I mean, you put that into a water heater. If you have a situation where you're heating water continuously, that can really back off the fuel usage, the energy requirement of the water heater, because you're already providing it with, pretty warm water. Good energy savings are available from the use of this waste heat to reduce boiler or water heater operating costs. Said that a couple times. Okay, so this is this picture is cut out of the DOE Compressed Air Challenge literature. I'll have a compressed air reading file like we've had on steam and pumps for you coming out shortly. In fact, I may just tag it on the email today, give you something to think about. Start reading at your leisure. But you can see this is a little more detailed than kind of the cartoon that we had on one of the early slides. So, but again, we see two compressor boxes. This would be lube injected rotary screw compressors. Motor, this is the actual compressor, got an inlet filter. We're spraying lubricant in to the air as it comes into the compressor. This is the air oil separator. There's an element in here. Oil falls down to the bottom. It goes back over here to the heat exchanger to get cooled off, and then goes back into the compressor. We have our compressed air coming out of here. It's hot, hopefully mostly oil-free. Goes through the other part of the heat exchanger and then comes out to the system. We're showing the supply line. Notice we do have these kind of long radius elbows coming in here, which is a best practice. We'll talk more about that in the piping portion of the discussion. We're feeding down here. This would be a valve to be shut because we would want to go through the dryer. We got filters, moisture separators, and I'll show all of them here. Would come back up, compressed air storage tank to have some air stored to kind of smooth out the pressure fluctuations. You have, different air tools coming on, going off, uses of compressed air. So that pressure will jump around a fair amount. And the more air that you store in receiver tanks, the more you can kind of smooth that over. This is a pressure flow controller, or a demand expander, as it's called. And this thing will set the pressure downstream of it, plus or minus about 1 psi, so long as you have some air stored upstream. We'll talk more about this. When we get to our main plant distribution system, which again we show as a loop, because if you have a big use, say down here someplace, you can actually make up air to that area from two different directions, and that again minimizes pressure fluctuations in the system. Pneumatic tools. These are called FRL stations: filter, pressure regulator, and lubricator. Sometimes the equipment here needs a little bit of oil to be sprayed into it to lubricate the device. So that's what that's referring to. Okay. So we're going to talk about all these elements in pretty good amount of depth and detail. Okay, so the old adage in energy management is you cannot manage what you do not measure. You can't just look at things and know what the heck's going on most of the time. So what in a compressed air system, what might we want to measure? Well, how about compressed air flows? How about system pressures? How about compressor power usage? We can try to find and quantify leaks and ultrasonic leak detectors. And now we have even kind of visual type leak detectors that I will bring one of those to class and demo it. Oh man, we can have dryer pressure loss and filter pressure losses. And, we want to be able to monitor all of the components in the system because it's possible for them to get clogged up with debris or crud and increase the pressure drop significantly. And so then the usual response to that is to up the discharge pressure on the compressor, which then increases the power bill even more than it was before. Okay, so let's look at a power flow diagram, kind of similar to what we saw this similar diagram for pumps, and it hasn't really changed very much, but we need to look at it for air compressors. Motors are rated on output power, thus a 100 horsepower motor can deliver 100 brake horsepower to a load at full power. Now, what we see air compressor manufacturers doing is putting motors on things that have a service factor of 15% typically, and they will design the full load power requirement of the compressor into the service factor, which means they might have that compressor pulling 105 to 110 horsepower on a 100 horsepower air compressor that has a 100 horsepower motor. Now, so long as you keep this motor cool enough and you don't exceed the rated service factor on the motor, you're probably going to be okay. But that's how far they push it in terms of performance and keeping the cost down on the air compressor, because there's quite a number of good compressor manufacturers, and it's a pretty cutthroat industry as far as selling the compressors and being competitive in cost. So at any rate, we have electrical, we're showing three-phase power coming into the motor. We have some efficiency on the motor. So then the motor input power times the efficiency on the motor gets us the shaft brake horsepower going to the compressor. And then if we know the, and this should be a C, copy this slide over. That's the efficiency of the compressor here. I got a C here and a P here. This P should be a C. I always forget to change that. In fact, I'm going to change that right now. I've been meaning to do that for many years and keep forgetting. Okay, well, that's a little better. So this shaft brake horsepower times the efficiency of the compressor would be the increase in air energy from the inlet to the outlet. And we say that's roughly 20% of the brake horsepower that comes into the compressor actually appears in the air after we cool it down, and we typically reject that 80% of the heat to the environment. And if we put a lot of compressors these days have variable frequency drives on them, and so if we tag a VFD on there, it's going to have its own losses. We would say typically 2 to 4% of the input electric power. I guess in some cases at really low load, it may even be higher than that. But at medium to high load, I'd say 2 to 4% is probably a reasonable estimation. So that's an additional efficiency or inefficiency. So if we look at the air power over here, then if we start dividing by the efficiency of the drive, the efficiency of the motor, and the efficiency of the compressor, we can back ourselves up to the input energy that's going into the VFD. That's what we have to pay for. Okay, specific power, I mentioned it before, so this is a little more about that. Let's see, so 100 horsepower compressor is rated to produce 450 CFM. So, it depends on the manufacturer. I usually encourage students to memorize some number. I would say between 420 and 500. There are some 100 horse compressors out there that at 100 PSI are rated for 500 CFM. That's fine. My number I remember is typically about 450, but whatever you want to, but you need to remember that a 100 horse compressor for a standard industrial compressor is roughly 450 to 500 CFM. So at full load, the motor puts out 110 brake horsepower, typically, because we're 10 horsepower into the service factor. So we're running 10% over the motor rating, which in this case would be 82.1 kW. I think, let's see if that's 0.746 times. Yeah, that's a direct conversion. So then to get the motor input power, you'd have to divide that by the motor efficiency. So we say the manufacturer has designed into the service factor. Yeah, there we go. If the motor is 95% efficient, then the motor input power, not shaft power, is 115.8, which is 86.3 kW at full load. Specific power is a measure of the efficiency of the compressor to produce compressed air. As we said before, we can do it in terms of brake horsepower per 100 or kW per 100, or you can do it brake horsepower per 1 CFM. The number is a little more palatable if you do it per 100. We typically see numbers probably between 16 and 22, something like that, in terms of kW per 100, and a little bit higher in terms of brake horsepower. So this can be calculated, and you can do it on motor input or output power, depending based on whatever your desire is. You just need to be consistent in doing that. Using motor input power gives a measure of the total cost of producing compressed air. So for example, for this compressor stated up above, that's 10% into the service factor, it's pulling 86.3 kW at 450 CFM, so 86.3 divided by 4.5 hundreds is 19.2, which is a typical full load efficiency for a lube injected rotary screw compressor. At part load, if this compressor was modulated back, as we'll see, this number will go up because we start losing efficiency as we operate at less than 100% capacity. Okay, so where do we get data? Well, I think we might have even seen the same slide in the pumping presentation, but there's a 450 horsepower motor rated at 1785 RPM. At 460 volts, it'll pull 488 amps. And it's got a service factor of 15%, rated for continuous duty, 60 hertz, power factor 90.5, max kVAR 70.2, And so just to show, if I take rated amps, rated volts, square root of 3, power factor, and motor efficiency, it comes out 450 horsepower, which is what you would expect. This is some log data. We'll be pulling some up. I've got lots of data logged on different air compressor systems, and so we'll be looking at that. This is showing, let's see, this is the amps. This was I think this was like a 500 horsepower compressor. This is a big compressor, okay, and this was a fairly complicated system. It had more than one compressor operating, but this shows the amps on one compressor, and this shows the pressure in the system. And this was actually kind of interesting because what had happened is at some point during the evening, an air compressor got turned off, and we really didn't have, during this initial period, really didn't have enough compressors operating. And you see, this is on pressure. This is the upstream pressure right at the compressor, and this is out in the plant someplace. And we see this, this is the normal pressure pattern. But back up here earlier, we didn't have enough compressors. And so the system, we were, this is running up here, between what, 100 and say 115, bouncing up and down. This is a controlled band on an air compressor. And so we see that this pressure, golly, it got down to 80 when they wanted it at least 20 psi higher. And so all of a sudden somebody discovers that, oh my gosh, we need to turn on another air compressor. And they do, and then we kind of return to normal operation. They did have a demand expander on this thing, which actually, yeah, this is upstream of the demand expander, and this is downstream. And then at some point here, the thing kind of started going haywire. It looked to me like we had a control issue or something on the demand expander. But anyway, see that demand expander, maintains a pretty constant downstream pressure from the device. And this was what the compressor, we had a compressor that was running in load, unload mode that was pumping up and down roughly between these pressures. So anyway, we use lots of data loggers looking at electrical current into the that's required by the motor and the pressure in the compressor room and then out in the system to analyze compressed air systems. Okay, so, are we going to measure electrical current or power? You guys are pretty good on this. Now, you've seen this power equation, RMS, volts, amps, power factor, square root of 3 divided by 1,000 is kW. And we simply have to come up with these measurements, or we can put the power meter on and measure the power directly, which tells us the actual power factor and all, which is better. And again, this is the background information in PSAT, which is a handy place to go to get electrical data. And this shows an actual power meter screen when taking, this is just different. This is the volts and amps, and then this is the power screen. So these volts and amps were producing, was slightly different because, you had to change the settings, so it might have changed a little bit. But anyway, these are the three phase-to-phase voltages. These are the three currents, and this was the power that we were seeing on the meter. This is the kVA. So this is the hypotenuse of the power triangle. This is the cosine side, and then you can calculate the k-bar from these two. And the ratio, 73 divided by 93.2, should be about 0.783, which is the power factor. So that's pretty good. Okay, compressed air generation, that's probably a good place to break off on this one. So I'll get this distributed to you along with the slides, and you know, we do need to start thinking about a test. We're probably 10 days away from our second test, which will be on pumping systems. So I'll be back in touch shortly. Hope you guys have a great day. Bye.